Hello! Welcome to my new series, Chemistry Cheat Codes.
This is a series where I will offer up an explanation of the theory and purpose behind many of the challenging problems in science and engineering classes. This particular series will be focused on general chemistry lab. Firstly, I am a student of mechanical engineering and an undergraduate teaching assistant responsible for overseeing a lab. I am not a professor, and I am not a graduate. The purpose of this series is Chem Lab success. I'm going to try to give you insight into Chem Lab from the perspective of a TA. The series will be organized into episodes which correspond with specific experiments. Episode 1. The experiment everybody overlooks. If you attend a typical university, taking a typical general chemistry lab, Experiment 1 will be a seemingly tedious and meaningless exercise where you are forced to relearn how to use things like rulers, graduated cylinders, and balances. You will learn about lab safety and sig figs, and you will probably be asked to complete a few seemingly meaningless measurements, and pretty much everybody, including the TAs, treat it as free points day.
Nevertheless, there are three main objectives that TAs and lab professors are trying to communicate in Experiment 1. The first one is Chem Lab basics, such as safety. The second is proper measurement technique. And the third and most important one is error analysis. In order to understand the reason why we spend an entire day of lab focused on error analysis, we first must beg the question, what is the goal of science? The answer is to explain. When you think about the work of scientists, it boils down to seeing an unanswered question in nature and seeking to tackle it so that the new understanding can one day better society. These explanations are imperfect by nature, and the secondary goal of science is to continually improve these explanations that it produces. So if the goal of science is to explain, then models are the road to explanation. Let's quickly talk about models. My favorite quote about models comes from a statistician named George Box. He said, "All models are wrong, but some are useful." A model is simply something that scientists and engineers use to make predictions. Some quick examples of models include the model of the atom, the concept of energy, the economic principle of creative destruction, and the theory of evolution, to name a few. What all of these models have in common is that they are extremely useful in predicting natural phenomena, but all operate using assumptions that are not universal, and so they are bound to have error. A few pros of models is that they are convenient, usually accurate, and help us understand the world. The one big con is that error is always present, hence, all models are wrong. The big idea is that there's what your professor tells you in lecture, and then there's what you're actually going to find in the real world. Chemistry lab is going to be your first college experience where you're going to have to cope with the discrepancy between idealized prediction and reality. What you have to understand by the end of this lab is that models are what we use to analyze nature. Even density is a model. You may not think of it that way, but that's what it is. It's a useful model for us to take into account in various problems how closely packed atoms are in a substance. When you use water displacement to find density, these are the assumptions you make. 1. The substance you are measuring is incompressible. Think about it. If what you were measuring was compressible, then when you subjected it to the pressure of being underwater in the graduated cylinder, its volume would certainly change, which would change the density. 2. You are assuming that there are no pockets in whatever you are measuring that might have air in them. 3. You are assuming that the temperature in the room is constant, because as we know, volume is a function of temperature, which makes density a function of temperature. And honestly, the list could go on and on. Does this mean that we give up? No way. We still need to extract meaning from a world riddled with ways for experiments to go wrong. We do that with scientific tools and terminology. First, Whenever we can take measurements with accurate devices, we use those devices. Secondly, we are constantly on the lookout for where our assumptions are not valid and are producing error, and we work to mitigate them. For example, with the density assumption that our material is incompressible, this usually won't be a problem in chem lab, so it's safe to say that this assumption is valid. However, the assumption that it might have air pockets, you bet this is going to be a problem. You might need to cope with this problem at some point. Third, and most importantly, we remember that in science, we are not alone. We use proper sig figs and proper terminology to communicate our error to others so that they might help us resolve it in their own experiments. In short, this is the furthest thing from free points day. Sorry. This concept of discrepancy will not go away. In fact, it is arguably one of the most important concepts we will discuss all year in lab. We're going to ask you questions like, is your answer precise? Is your answer accurate? And how could you mitigate or resolve the error in this experiment? And answers like yes, yes, and yes are not going to be acceptable. And how about this task? Discuss your error. Answers like human error are not going to be acceptable either. Instead of just a yes answer, you can answer questions like, is your answer precise? Like this. Yes, my answer is precise because I performed the reaction 6 times and I measured the mass of the products and my percent relative standard deviation was less than 1%. This is a good answer because the term precise was used correctly and that the experiment was repeated many times and a similar answer was produced. It is also a good answer because this person backed their answer up with some statistical analysis. It is an argument for why the answer is precise, which is excellent. Obviously, this is a very general answer, and in a real lab question, you should be more specific about what the experiment actually entailed. Discussing error involves looking into your experiment and finding where your assumptions produced error. Once again, saying that you had human error is not acceptable. Everybody has human error. You could say that there was error within your experiment because the reactants in your reactions were not completely reacting with the products, which caused your percent yield to be 68%. Also say why you think this is true. Give evidence for the error. Don't just say whatever comes to mind. It is also impressive to include a way to mitigate the error. Remember that the goal of science is to explain. If we allow error to play such a dominant role in our data and studies that it skews the data to meaninglessness, are we really doing our job? The reason this experiment is so important is that if you understand it and learn from it, you will do better in all of your other experiments as you will be less callous in your methods and your data will turn out to be more precise and accurate. Thank you for joining me in this installment of Chemistry Cheat Codes. I hope to see you next time for episode 2. And for a new perspective on sig figs, stay tuned for my After the Credits scene extra credit. Sig figs seem annoying and can be a pain. The rules sig fig calculations follow also seem arbitrary. Hopefully, this segment will change your mind. Smiley face. For the purposes of this segment, let's pretend sig figs don't exist. Nice, right? Let's quickly carry out a calculation without regard to sig figs. Let's say we want to add 0.23456 and 0.32. We can either plug this into our calculator or do it by hand. Either way, we're going to get 0.55456. The number 0.32 varies in the hundredth place. By the definition of sig figs, 0.3 is what we know to be true, and the 0.2 is a guess. This means that this number could have also been 0.39 or even 0.30. This variation carries on into our final answer. Our answer then becomes 0.55456 plus or minus 0.05. Our answer could vary by as much as 0.05. Thus, the digits to the right of this variation would be wiped out. Thus, for the sake of simplicity, it is safe to say that we can eliminate them. And our new answer becomes 0.55. I hope that you can see that even if we don't use the sig fig rule that says that if we do a calculation that is addition or subtraction, we limit the number of sig figs to the lowest decimal place, we will still end up with the same answer. That is because the sig fig rules were not just contrived by some old scientists, they were derived from logic.